Hi, welcome back to my YouTube channel. Hope you are doing well. So, if you can remember what we are working on, we are actually simulating this model. So, in our last video, I explained how you can add materials. Okay, we already generated the geometry of this paper actually, right? We draw this geometry and then we add all the materials, right? Here gold and silica and analyte. And then we add physics, then we did the mesh and and then we simulate the model and this we got this kind of horizon like this, right? So now what we have to do, I told you that we will reproduce this graph actually. So let me explain what the graph is actually. Okay. So here, okay. So here you can see that this is the graph and this is the phase matching curve actually. So from here, okay, you can see that they simulate the model from 600 nanometer to 800 nanometer, right? And for the temperature, we have to search for which temperature they simulate it. So this is the result section. Okay, the last mention here. Okay, in figure 2. Okay, yeah. They simulated for 20 degrees Celsius. So yeah, this curve is for 20 degrees Celsius, and this is the effective index, and okay, and this is the confinement loss. They put the confinement loss in the secondary axis, and in primary axis they put effective index. Okay, it's okay. So yeah, so we have to simulate our model from for 20 degrees Celsius, from 600 nanometer to 800 nanometer, right? So the light pass through the fiber from 600 nanometer to 800 nanometer right now. Okay, so for that, what you have to do in parameters, okay, no, sorry, from not this parameter, from parameters 2, we have to define the temperature as 20 degrees Celsius, okay? So yeah, it will change the value of Na. Okay, so it's a 1.44 now when it is 80 degree, let's say, and then when it is 80 degrees Celsius, then Na is 1.40, but when it is 20 degree, then it is 1.44, right? So yeah, it's okay. So what we have to do now, we have to simulate the model. Okay, let me check. We put 20 degree, it's fine. Okay, now from study, we already simulate the model, but we don't need the result now, so we can delete the result from here. Okay, okay. Then from study, we have to choose parametric sweep, and from parametric sweep, we have to okay here from here we have to select add. And then it will be L. Actually, this is the wavelength, right? We know this is the wavelength. So then you have to click here, and then you have to click on range from 600 nanometer. Step size will be 10 nanometer. It's fine. And stop for 800 nanometer. Okay. So yeah, well, it's perfect. And in mode analysis, okay, this is okay. Everything is fine. So, yeah, we are going to simulate it. I think we will get the results. So, we can compute it right here. So, it will take some time. So, we have to wait for iteration. Okay, so what is the phase meshing curve actually? If you know that what is phase meshing curve, then we will understand why we need this phase meshing curve actually. So here you see that we are simulating this model for from 600 to 800 nanometer, and the uh, uh, wavelength shift also 10 nanometer, right? So we are not taking wavelength shift 1 nanometer because it will take lots of time. You can take 1 nanometer wavelength shift. It's okay. It will be more good then. Okay. So what is the this phase meshing curve actually? So phase meshing curve. This is the confinement loss curve. Okay. And here you can see then this yellow line is Y polarized SPP mode, real part of Y SPP mode, and this is the real part of core mode. Okay, and you can see that the real part of SPP mode and the real part of core mode is meshing at the same point, right? At the point where we okay, the real part of core mode and the real part of SPP mode. Connect in a point at the wavelength where we got the maximum confinement loss. So this is a way you can calculate, or you can just get the maximum confinement loss. Okay, so um, uh, this actually phase meshing curve prove that your conformal loss curve or your resonance wavelength is correct, 100% correct. That's the thing. Okay, so yeah, that's why we actually calculate the phase meshing curve. Okay, and another thing here you can see that they simulate at least like 5 temperature from 20 degrees Celsius to 60 degrees Celsius. Okay, but they only mention one phase meshing curve for 20 degrees Celsius. They didn't mention the phase meshing curve for 80 degrees Celsius or 60 degrees Celsius. In your case, you can mention all the phase meshing curve. It's completely fine, but it will take lots of time. That's why people usually take one phase meshing curve. It proves that's okay. You are doing perfectly fine actually. So your calculation is fine. That's the thing. That's proof that your calculation is fine. Okay. And if you can show all the phase meshing curve in this curve, then it will be more good for your case. Okay, that's the thing. So yeah, okay. This is actually confinement loss curve from 20 degrees Celsius to 60 degrees Celsius, and this is amplitude sensitivity curve from 20 degrees Celsius to 50 degrees Celsius. Okay, so this is refractive index sensor. Okay, that's good. So yeah, uh, photonic crystal fiber-based space sensor is actually refractive index based sensor. Okay, so we actually measure here refractive index uh, using um, temperature sensitive liquid, right? So yeah, it's not you cannot differentiate it from um, like biosensor or something like that. Okay, the simulation is working perfectly. Progress is 72%, so it's almost done. So you can see that the simulation error is kind of low, 10 to the power minus 8 to 10 to the power minus 6. So yeah, this is the error and iteration time number. So this is the iteration like one iteration to yeah 6 Okay, 53 to 63. So it required 10 iteration to get the um, below um, uh, desired number of um, uh, error. Okay, so uh, I think you already know Newton-Raphson method or finite element method. So what they did, they actually um, take some kind of iteration and trial and error, right? And then they finally, it's not 100% a perfect result, but yeah, they try to minimize the error, um, right? So there's a thing that's this solver actually working. It's actually trying to minimize the error. Okay. Here you can see that in some in some point of iteration, the error is increasing, and some point of iteration, the error is decreasing. So, um, sometimes you see that in your model, the by increasing iteration number, the error is going to increase and increase and increase, not decreasing. Then your solver will show some errors. So there's a thing that your solver cannot solving the problem, or you do have some you may messed up with materials property or in physics or mesh. So you have to find out the problem where you uh, messed up actually, then your solver will work perfectly. So yeah, it's almost done actually. Yeah, I got the more results. Okay, yeah. So for to get the mm, results actually, we need arrow surface. So make sure that in arrow surface you select from present, and as well as surface you have to select from present. Okay, so then you can work from electric field. Okay, so this is y polarized mode. And yeah, this is x polarized mode, and this is y polarized mode, and they are actually SPR mode. Okay, SPR mode, y polarized mode. Yeah, so you can see this is y polarized mode, and this is y polarized SPR mode. Okay, so yeah, it's complete fine. We are going to start from 600 nanometer. So this is 600 nanometer, and we have to find out the bipolarized mode, because uh, in this paper you can see that they are working on bipolarized mode. Okay, so it's tough to see that you can sorry. Okay, so you can see that this is actually bipolarized mode. Also, they are actually working on bipolarized mode. And they also mention here this is y polarized mode. Same, the curve, the conformant loss curve is actually for y polarized mode. So that's why we have to do it for y polarized mode. So let's okay, uh, yeah. So to get the results, we have to find out the y polarized mode. Okay, okay. For 600 nanometer, this is y polarized mode. Okay, let me mention. If polarization is negative direction of dipole or in positive direction, is completely fine. So it's not a problem. Both are polarized light. Okay. Whatever it's in positive direction or it's in negative direction. Okay. So yeah, to do that, we need another Excel file. So I think I need to open an Excel file. Mhm. Okay. Oh, I'm sorry. I have to share the screen for Excel file, right? So I'm sorry. I think you are not uh, getting the Excel file, right? So I have to share it. Okay. So now maybe it's working. Yeah, this is the Excel file. Okay, I'm sorry. Okay, this is the Excel file. So we need this Excel file. In Excel file, we have to define wavelength WL from 600 nanometer to uh, okay, is equal to 600 nanometer plus 10. Okay, 800 nanometer, right? So we need a wavelength from 600 nanometer, then to a 800 nanometer, and then this will be actually effective mode for temperature 20 degrees Celsius, right? And this will be confinement loss for temperature 20 degrees Celsius. Yeah. Um, Initially, we need this kind of thing, and then in COMSOL, what you have to do, you have to collect this data. Okay. So to collect this data, you have to go through drive values. So from drive values, right click, and then you will get global evaluation. So from global evaluation, you have to click on global evaluation. Then in expression, before taking expression, let's select this one. From study, you have to select study one parametric solution. Okay. So from parametric solution, also you have to do this data only. From data only, you have to select outer solution. Okay, and then from expression, you have to click on here. So then, okay, let me tell you again from uh, replace expression. You have to click, then electromagnetic wave, then sorry, we will get from global. From global, you will get a effective mode index. Okay, so this is ewfd.neff. So if you don't want to go through this equation panel, you can just write ewfd.neff. It's completely fine. You can write ewfd.neff. Okay, so then we need to stop. We need to just make it small. Okay. Okay. So now, just what you have to do? Okay, we select study parametric solution, and then select parameter solution L, um, all. Okay, and effective mode all. Okay, and then from evaluation, you have to click on evaluate. So it will take some time. Okay. So it's provide you all the data from here you can see that from 600 nanometer to 800 nanometers. So and in this column you will get sorry, in this row you will get the wavelength, and in different column for 800 nanometer, in this column you can see that you will get 8 mode, right? Because we are searching a different mode. Okay, so we need the design number of mode. So here you can see that there is 8 different mode, right? So if we just make it okay, so then you can see that this is 8 number of mode. Okay, there's nothing. From this 8 number of mode, we have to search our design mode. Okay, so that's our actually goal. Okay. And yeah, and make sure you are selecting this one full precision and auto. Okay, you have to make sure this one. Sometimes for your case, maybe it's automatically select this one or this one. Then you will not get 100% correct data. So you have to select auto and full precision. Okay, that's the thing. Now, here you can see that effective mode index is this one, and for 600 nanometer. Now let me search that if this position of effective mode is working for other wavelength or not. Okay, so here you can see that you can change this panel actually. So yeah, if you can change this panel, so the if the I don't know the color is the color is maybe uh, it's kind of maroon, right? Okay, this is maybe kind of maroon color, right? So if this maroon color bar is in below, then it will change the mode on this. This is the effective mode is in below, right? So it will change the mode, and if it is in up, then it will change the wavelength. Okay, so we are fixing the position of effective mode, and now we want to change the wavelength. So if we are taking it up, right? So then if you click here, then it will change the wavelength, but not the position of the effective mode. Okay, so that's the thing. So here you can see that the position of mode is from bottom is 3. Okay, and here you can see that selected mode is from bottom is 3. So, but it's changing the wavelength. So here you can see that for 600 nanometer, our desired okay, our desired mode is position is at um, mm, uh, from the bottom is position 3. So but uh, for the next wavelength is the position is not at 3, right? So we have to take the data for 600 nanometer. So here you can see that this is the position 3. Okay, so then click here, right click. So first click here and then right click and then copy cell to clipboard. Okay, we are going to copy this cell actually, only this cell. So, and then you have to go to the Excel file. So, this is actually effective mode for 600 nanometers. So then Control V. So, yeah, we collect the data for 600 nanometer and then for 610 nanometer. So for 610 nanometer, this is not the mode actually. Then you have to put it down and then you have to search the uh, digital mode. So this is the digital mode at the position of fourth from the bottom, okay, or from the top, its position is fifth. Okay, so let me see if for next wavelength if the position is the same. Okay, for from 610 to 630, the position is same. From the bottom, it's fourth. Okay, so from the bottom, the fourth one, right? This is the bottom from the bottom. Okay, so then for that case you have to click on this and click right, and then you can click copy. Okay, no, sorry, copy selection and headers to clipboard. Okay, so then you have to go to the Excel file, then you have to Control V here. So then you can select this three and Control C, and then click here and then right click, paste special, then transpose, and then okay. So, okay, I've got all this data. Okay, and then make sure that you are not copying anything here. Okay, so for that case, you can click escape, ESC from the keyboard. Okay, Okay. And then we have to search for next wavelength. So it's for 640. So where our desired mode? We need to search where our desired mode is. Okay, this is okay, from the top, its position is fourth. Okay, no problem. So let me see if okay. So for it's only for 640, right? So that's why we have to go through this way. Okay, and for 640 from the top, its position is fourth, right? This one actually. So then copy cell to clipboard and then go to the Excel and then Control V. So yeah, and then for 650, we have to check. Okay, for 650, it sends the position for maybe it's not web polarized. I don't know. It's difficult to understand if it is web polarized or not. So let me take the data for 650 first. Okay, its position is from the bottom, its position is fourth. Okay, or from the top, its position is fifth. So for 650, right? I'm sorry. For 650, the position is fifth. From the top or from the bottom, it's fourth. Okay. So copy cell to clipboard. Okay, then paste it here. Control V. Okay, and then let me see for 660. So yeah, this is explorize. Okay, okay, I got it. This is actually Y polarized, but the thing is, uh, maybe this is actually I don't know why this kind of thing is showing, but this is showing that this is actually Y polarized, right? Okay. Mhm. So you have to take it as Y polarized, right? There is no sense to mm, think about it. Okay, so then for 670, okay, and then Y polarized light is working perfectly fine, but for 660, it's kind of messed up. Okay, so um, so okay, they are not changing the position now, so it's very good for what the steering happened to it. Okay, so so till for 740, its position is same. From the bottom, it's fourth. So from the bottom, its position is fourth. Okay. So let's take it. Copy, take selection and header to clipboard, and then you have to paste it here. Control V, and from 660 to 740. Okay, 660 to 740. Okay, then Control C, and then you can paste it here. Paste a special transpose. Okay, and then click Escape. Then it will not copying yet. Um, okay, so for 750, we have to find out the okay. So this is at position 3. Mm. So yeah, uh, this position is 3, third for uh, So selection to report. Okay, then paste it here. So from 750 to 800, right? From 750 to 800. Yeah, Control C and paste special transpose, and yeah. So yeah, we collect all the data. So now we have to calculate the confinement loss, right? So we have to write the equation of confinement loss. So the equation of confinement loss, it will get you will get this is the actually equation of confinement loss 8.686 into 2 pi into imaginary part of effective mode into 10 to the power 4 divided by lambda. Yeah, that's fine. So I already do have the equation maybe. So you can write it this equation actually. Okay. Okay, this is actually the equation. So 8.686 into 2 pi, this is 2 pi, and the imaginary part of the effective mode B, this is B2. Okay, and then divided by wavelength into 10 to the power 4. Okay, so was 10 to the power 4 with this actually. That's why if we put down, then it will 10 to the minus 4. If we take wavelength as in micrometer, then it will be 10 to 4. And if we take wavelength in nanometer, then we have to take it 10 to the minus 7. Okay, that's I think. So in our case, the wavelength, sorry, let me check. Yeah, okay. So scroll down, then yeah, what's going on actually? Okay, it's not working fine actually. So um, it's actually messed up. I don't know why. So for our case, the resonance the resonance wavelength must be 697, but here in you for our case, the resonance wavelength is at 650. Okay, 97, right? So first resonance wavelength at 650, but it's again increasing, so uh, we'll get another resonance wavelength. So that's the thing. So yeah, I don't know why it's working like that, but yeah, it's working like that. Oh, another thing I want to mention. Their loss is till 2050. Oh, sorry, 250, right? Decibel per centimeter. But for our case, it's only 19.90, 19.19 decibel per centimeter. So that's another issue. maybe it will increase and increase till mhm. It's not the correct data, right? Let me do it again. It's the same sheet, right? Yeah, you can see that it's the same sheet if you change the equation. So I don't know. Um, but yeah, it's working. That's like good point. That is actually working. And another thing is another thing is uh, it's shifting up. So maybe we'll get another resonance wavelength. But the problem is dimension. We must get the resonance wavelength at around 700 nanometer, but we are not getting resonance wavelength at around 700 nanometer. We are getting resonance wavelength, fast resonance wavelength around 600, 650 nanometer. So that's my point. So the problem is, I can mention the problem actually. The problem is they are actually they define the gold parameters of gold, but they didn't mention it well actually. Hmm. Okay, let me search actually what's the problem behind the thing. Um, we take 600 and 10 nanometer. No, this is completely different thing. Yeah, so the problem is 20 to 60, right? Okay, I got it. Mhm. So here you can see in their model actually, I got it. So the refractive index of this red curve is actually 1.36, right? 1.36, and its resonance wavelength is around 700 nanometer. And for this case, it's actually the same shape. But okay, huh. So the problem is in our case, we define the same thing, but okay, but here Na is actually 1.44 for 20 degrees Celsius, right? So, that's the problem. Maybe in our, it is actually minus. I'm sorry. I'm sorry. I wrote it wrong. This is a minus. Mhm. And the value of n, okay. And the value of n naught is, I'm sorry. I mentioned all the things wrong. I'm sorry, guys. Super sorry. Now it's fine. D naught and dn. Uh, it's not negative. It's 3 point. Okay, 3.9 4 into 10 power minus 4, 3.9 into 10 power minus 4. Okay, 3.94 into 10 power minus 4. Okay, and like you can just write it E. Mhm. I'm sorry, I messed up actually. Oh, I'm sorry, I messed up actually. In for defining um, parameters. Okay, so I'm sorry for that. So now it's okay. Now it will work actually. Yeah. Um, we got it. I think you got it right, or what you did wrong. Okay. So we did wrong for DN. We did wrong for N naught, and that is the thing. So now, okay, as I mentioned you that for refractive index 1.36, this is the red line, and you can see that this is the refractive index 1.3605. It's kind of 1.36, right? So yeah, then you will get this the data. Okay, so now you have to I'm sorry for misguiding you actually, I'm sorry. Now you have to again simulate this thing. Same way as I simulate for uh, previous case. Now you have to simulate it again, and then you will get the perfect data actually. So maybe I can do it for you. Okay, if you can just wait. Okay, then compute again. Mhm. So I'm pausing the video for now till the simulation is done. Okay, thank you. Hi. Okay, the simulation is done, right? Yeah, the simulation is done. So let's see again the same thing. Okay, from sorry, from 600 nanometer. Okay, so this is the Y polarized light for 600 nanometer. Okay, here you can see that confinement loss is very high. Okay, okay. Oh, I'm sorry. So here you can see that the confinement loss is very high. So how do you have to do? You have to calculate the data again. So from global evaluation, you have to evaluate the thing again the same way. Okay. If you want to watch this video till now, you can watch or you can do it by yourself actually. It's the same thing as I did before. Okay. Okay. So the position is third. Okay. For 600. Let me check for. Okay, let me collect the data for 600 first. The position is third. Okay, paste it here. Okay, I'm sorry. For 600, click here. Control C, copy clipboard. Control V. Yeah, you can see that the loss is very high, 135. So in the paper, you can see that for six, oh my God, for 600 nanometer, the loss is not that much high actually. Mm-hmm. Yeah, I don't know what's the problem is. 1.3, 2.3, this is 2.3. Yeah, this is perfect. Okay, I don't know. I don't know the things. Mm, mm-hmm, mm-hmm. Let me check just. Okay. It's tough to understand which one the core and which one is the SPP. Here you can see that both are kind of similar, right? So it's very tough to understand which one is the SPP or which one is core. But yeah, the problem is what it's saying that it's the resonance wavelength. Have you got it? It's saying that it's the resonance wavelength 610, but at 610, we didn't expecting the resonance wavelength. That's I think. I'm sorry, not this one. Sorry. Mm-hmm. Okay, that's the problem actually. In material property, maybe we messed up. We have to check again. Mm-hmm. For gold, it's actually 9.48 for gold. Okay, 9.75 for 8. Okay. It's not that much problem actually. 4875. Okay. 1.36 into 10 power 16 omega. Omega is actually 1.36 into 10 power 16. Yeah, that's fine. Omega C is actually 1 point omega C. They didn't mention omega C. That's their problem. Okay. They didn't mention everything perfectly. That's their problem. Okay. So, but yeah. We mentioned omega C 1.45 into 10 power 14. Mhm. So then we calculate all the things. And as well as for, mhm. light. Okay, they are the wavelength of incident light. Okay, and are the constant of Selmer. What is this? The base material is okay. It is material depend on the main equation. So yeah, we wrote this equation, but they didn't mention any Selmer coefficient. That's another issue. Uh, uh, so I first of all I mentioned you this paper is kind of not good actually. I'm pretty much sure this paper is must not good. That's why it's showing lots of problem actually. Um, the property of silica, as I know, it's completely fine. Mhm. B on B2, B3, C on C2, C3. Square root of 1 plus. It's completely fine. It's not a problem actually. This equation is temperature sensitive. Oh, I got it. Okay. They didn't take the temperature sensitive base silica. It's a problem. So in temperature sensor, obviously you are taking some temperature dependent liquid. So in the outer thing, you will change the temperature. So the temperature will affect the refractive index of the silica, obviously. So you have to take temperature sensitive equation of silica, right? But they didn't take it. They take the normal Selmer equation. So that's the problem. Okay. So that's the problem. But our calculation is fine, completely fine. So yeah, you can do the things. Yeah. Okay. So this is completely fine, and I can tell you that 610 nanometer is the resonance wavelength. So you have to calculate other things as I did before in first part, but that was a bit wrong actually. But yeah, now it will be fine. Okay, so that's the thing. So thank you everyone for joining me. Yeah. So okay, we'll see. I'll see you in the next video. So till now, yeah, stay tuned. Goodbye.